He also worked as visiting professor at Rensselaer Polytechnic Institute, Troy, New York, USA in 2018. He is the recipient of Bhaskara Advanced Solar Energy Base Research Fellowship in 2018 by Indo-US Science and Technology Forum and Department of Science and Technology, India. He also has secured various grants like DAE Young Scientist Research Award by Board of Research in Nuclear Sciences, India, Young Faculty Research Award by SERB DST, and Indo-Sweden Bilateral Research Grant. His areas of interest in research are physics of thermoelectric and optoelectronic materials, 2D nanomaterials for future energy, and mesoscopic physics and nanofunctional devices. So with this brief introduction, I would like to invite Dr. Ajay Soni to deliver his talk. Dr. Soni, over to you, please.
Thank you, Professor Mishra and Dr. Rasaikar. So I'm thankful for your nice introduction, and it's a long introduction actually. I also wanted to thank the organizers for inviting me for this talk, and I'm excited actually to present my work. So what I'm going to talk today is on the light matter interactions in metal chalcogenides and technological applications. So my talk is more on the fundamental aspect of the metal chalcogenides and how the light matter interactions can give rise to the more meaningful information which can be used for technological application. So before I move to the second slide, am I audible clearly and my slides are visible?
Yes, sir. Your slides are visible and you're audible as well. Please continue.
All right. So yeah. So you know that light matter interactions are very important part of our day-to-day life, because whatsoever we are able to see in the nature, actually, the light reflects from the materials and then we are able to see them. And there are interesting phenomena which actually tells us about the various aspects of the materials as well as the intricacies of the materials for technological applications. So with your kind permission, Chair, before I move on to the technical part, I just wanted to give a brief idea from which part I'm talking actually here. So I am sitting here at the foothills of the Himalayas. This is the capital of India, and this is where you can see the Jaipur is. So this institute is a new IIT Mandi, which is 11 years old, and this is set up in the foothills of the Himalayas. And these are the two campuses. This is the North Campus, where most of the BTech curriculum is running, and this is the South Campus, where most of the PG as well as the research centers are established. And we have both the campuses are running very nicely, and this is the panoramic view of the campus there. All right. So in my group at IIT Mandi, we work on three basic areas: thermoelectric materials, graphene and functional devices, and optoelectronic materials. And our basic theme of the research is charge transport. And in thermoelectric materials, we work on several kind of materials which are environmental friendly, as well as high performance thermoelectric materials, where we can harvest the energy from the thermal energy. And we also do instrumentation for the customized research. And these are the publications from a particular theme, thermoelectric materials. And we also work on carbon-based and graphene-based functional devices, for example, the sensors for the fluoride detection in the water, as well as the patterning of the devices for the flexible electronics. We also work on the optoelectronic materials, like semiconducting material, which has a band gap in the visible region. For example, recently a lot of research has been going on the transition metal dichalcogenide. So one of the theme of our research is also based on the chalcogenide material. So majorly, if you look at like the overview, we work on the carbon-based material as well as the chalcogenide materials, and our research is generously funded by the various funding agencies. And so this is the outline of my talk. What I'm going to talk about today is how the light matter interactions gives rise to a very interesting physics of excitons in the materials and how you can use those excitons for the various technological applications. But what I wanted to include here is it's not just the materials aspect, but the materials processing as well as the characterization and how to extract the high level physics out of these materials as well as. So what we do is we normally look at the Raman and photoluminescence spectroscopy as a tool to understand these materials at an extremely nano scale, which is like atomically thin nanomaterials. So I have taken two examples of monolayer MOS2 and BZRS3 thin film. So these are dichalcogenides as well as the trichalcogenides. And if time permits, I'll go into the details of the photovoltaic in BZRS3. Okay, so when we talk about light matter interactions, you know that these are the phenomena you understand from your school level physics up to the master's level physics, where you have the light interacts with the materials, you have reflection, and transmission of the material. And once the light enters into the material, you have a lot of phenomena like the absorption and then the internal interaction of the light with the matter gives rise to the emission of the light and different colors, and you see a beautiful colorful nature surrounded by you. And so once the light enters, actually, and if you try to understand the light which is coming out of the material, you get a lot of information about the materials. And with those light matter interactions, you can do both kind of things. Actually, you can do a fundamental study like multi-body interactions. For example, you can understand the electron-electron interactions, you can understand the electron-phonon interactions, and you can understand the excitons in the materials. And so these are the basic fundamental physics aspect of the light matter interactions. Okay, and the technological application, if we talk about, this gives rise to a lot of interesting aspect of green energy like photovoltaics, light emitting diode, and solar thermoelectric devices, where the light has been used to heat up one of the end of the thermoelectric module. But what I'm going to confine my talk today is on the excitonic physics in the monolayer MOS2 and more on the chalcogenide materials. So let me just give you a brief about the chalcogenide materials, because I see some of the students are there. So if you look at the periodic table, the 16th group, right below the oxygen, you have sulfur, selenium, and tellurium. These elements are called the chalcogen elements, and these elements will make the compounds with transition metals or other elements in the periodic table as an anion. So those compounds, we call them as the chalcogenides. And similar to the oxide research, the chalcogenide research has vast spectrum of physical properties that includes like the materials have semiconducting to the semi-metals to superconducting and all kind of physics. If you wanted to understand, you can use this material to understand. And there are several phenomena which you are not able to see through the oxides. You will be able to see through the chalcogenides. So basic theme of the research is the chalcogenides in my group. All right. So the major part of the chalcogenides are that these chalcogenides exist in the layered structure. These layered structures equivalent to the, you know about the graphene, which is like a monolayer, a single carbon layer of graphite. So if you have a graphite and if you exfoliate a single layer of the graphite, you get a graphene. Okay, so these are the materials which are made up of the layers of the atoms, and the layers of the atoms are attached to each other by the van der Waals forces. So what I'm talking about is these are the monolayer, and there is a gap in between. This is the van der Waals gap, and this van der Waals gap actually exists in all these layered materials. And so what you can do is actually you can exfoliate, okay, down to the atomically thin layer. And once you exfoliate it, you enter into the extremely nanoscale, which is the atomic layer, and you have exciting physics as well as the exciting properties of the materials. For example, high surface to volume ratio and the electron and phonon confinement in these materials, and that gives rise to the exotic electronic properties. So graphene is a well-known example. Bismuth telluride, bismuth selenide is also a very good material to understand the topological insulators. And there are several materials like MnO2, hexagonal boron nitride, gallium sulfide, and Semitic clay, and there are several materials which are useful for the energy storage in the form of battery and all those. But what I'm going to talk today is the monolayer MOS2. which is a very, very exciting material because it has a thickness tunable physical properties. So if you look at the bend structure of MOS2, so this is the energy versus momentum. If the layers are large, let's say it is the bulk, what you have is it is an indirect band gap semiconductor, okay, and the band gap is 1.2 eV, which is close to the visible, which is in the visible region. If you remove one layer from the top and you put like 3 layers, the band gap changes. If you have the bilayer, the band gap changes further. If you have a single layer of MOS2, one molybdenum at the center, sandwiched between the 2 sulfur, you have a direct band gap. So what it becomes is direct band gap material. And once you have a direct band gap material, it has a very, very interesting optical properties, which includes the strong photoluminescence from the material. So this is the device on the WS2, which is a tungsten disulfide. Okay, and you can see here the fluorescent image. You cannot see anything other than that, the monolayer, and the glow is so large actually. Okay, so why it is happening actually? Once you are going from bulk to 3 layer to 2 layer to monolayer, what you are doing actually, you're creating a confinement of the electrons or the charge cases, which is equivalent to the quantum dots, like CDAC or CDS. In a basic quantum mechanics course, you understand, you study about the particle in a box problem where the energy levels are quantized, and these energy levels actually gives us to the various colors in the quantum dots, and this is where actually the confinement effect in these materials are very, very interesting. And because of this activity where the band gap is almost like 1.8 eV in the monolayer, it increased from 1.2 eV from the bulk, and it gives rise to a lot of interesting properties, and a lot of people have been using it for studying various technological aspects. For example, you can see last decade has been spent on making a lot of devices, a lot of new research from these materials that includes the phototransistors, photodetectors, heterojunctions, solar cells, and a lot of devices for the flexible electronics as well. And this is where the interesting aspect, okay. But you know that any new research or something, it doesn't go very easily actually. So you have a challenges. So the challenges are like, you can ask the question, if it is an atomically scaled thin layer, then how do you see? Because you cannot see the atoms through your eyes. And moreover, how do you prepare those nanosheets or the layers? Okay, and how do you make contacts? How do you characterize them? Okay, you need a high quality materials. So there are several challenges in this particular research. For example, preparation of the atomic scale nanosheets. And once you prepare it, actually, how to identify whether the nanosheets are existing at this place or not, okay? And then you need to find out whether the nanosheets, whether it is a monolayer or bilayer or all those things actually, okay? So it gives rise to a lot of questions, and that is where the interest lies for us, to understand the fundamental phenomena at this scale, and find out actually whether these materials can be used, like how to enhance their property for the technological applications. Of course, device fabrication is an aspect where a lot of people have been working. So in our group, we use the solution synthesis as well as the mechanical exfoliation of these layered materials using the Scotch-Tape method. So you see a lot of people are using mechanical exfoliation. There are people they use laser thinning of the material. Is like you put a high power laser on the material, so you just burn the top layers. What you have is only the monolayer sticking on the substrate, or you do the intercalation and then exfoliate it by the solution methods. In our group also, we do a lot of solution chemistry to understand. There are people who does the chemical vapor deposition to grow these films on the substrate. So you know that this is the image of mechanically exfoliated graphite, okay, graphene. So you can see there are different optical contrast here, okay, which shows there are different thicknesses of these layers. And this is again, like you can see here, this is chemically exfoliated film, and this is the quality of the film here. So like if you want a large scale growth of the film, the solution methods are better. But if you want a high quality of the material, okay, if you wanted to understand the fundamental physics of the materials, then the mechanical exfoliation will give you the high quality flakes or the nanosheets. So what you do is you just take out the crystal and exfoliate it using your Scotch-Tape, which is available in the market. Any stationery shop will have. And then you press it Then you take it out, and what you have is this is the silicon substrate, and on top of that the films are there. Now the difficulty is that once you have those films on the substrate, you need to find out where these films or where these flakes are. Okay, and that is where the difficulty lies, or the challenge lies in this particular research. And what we have done is, we understood the optical contrast method. Okay, and using that method, we have done some simulations to find out what kind of substrate you should use it. Okay, suppose if you are using the silicon dioxide, which is the most used substrate for the device purpose also, because you have a silicon oxide layer on top of it, so you can have a field effect transistor made up of you can fabricate a field effect transistor using this films. Okay. So the optical contrast method is very interesting. You know that on your screen, what you can see is there are some fishes actually with the different colors. So how do you distinguish between them? So what you do actually is you take the intensity of the yellow fish and the intensity of the white light from here. What is the difference between these two? Actually, will give you the optical contrast. Okay, and this is a very interesting aspect of the optical physics. Okay, and using that particular aspect, we have understood a method to find out the optical contrast, which gives us the idea about the thickness of the films. So what you see here is this is a silicon substrate with a dielectric constant something N3. Then you have a silicon dioxide, which N2, and then you have a nano layer of, let's say, MOS2 or WS2 or any kind of material which you want it. Okay, but the important aspect here is that the dielectric constant is a function of lambda. The incident light is very important here. So you can see the picture here on the right hand side. You have exfoliated flake. So you see this is a very thick flake. Now you can see here, this is the blue color actually. So which means from yellow to blue to purple to transparent or something. This is here. So this is what the monolayer is. This is bilayer and then trilayer and then the higher order of the layers. So what we do is we calculate the optical contrast. So as a function of the silicon oxide thickness, and so the y-axis is the lambda of the light, and the x-axis is the silicon oxide thickness. So what is the right thickness of the silicon oxide on the silicon substrate, so that you are able to see the nano layer very clearly on top of it. Okay, so we have done these simulations and we found out that there are some specific regions where the optical contrast is higher for the monolayer, and you need to choose the right kind of silicon oxide layer to find out where the monolayer is. Okay. So this is for the monolayer of MOS2. This is bilayer, this is trilayer, this is filayer. So these graphs are actually for the various layers, and the contrast value is shown on the scale here. So from here you can estimate actually where the monolayer is and what is the right kind of silicon oxide thickness. And this is not only for MOS2. One can do these simulations for the WS2 as well as WSE2, NBSE2. MOSE2, there are several materials. So what we have used actually is using this particular method, we have identified that, okay, the thickness which is close to the 60 nanometer to 100 nanometer, and another one is like 250 nanometer to 300 nanometer are the thickness of the silicon oxide, which is more appropriate for these kind of materials, especially for the visibility of the monolayers, especially in the yellow light here. So all right, using that actually we are able to see the monolayer, bilayer, and trilayer. And once you identify the flakes on the substrate, there is another technique called Raman spectroscopy, which shows the thickness dependence shift of the Raman modes, which gives you the idea actually whether it is a monolayer or it is bilayer or something. So what you see on the screen here is that there are peaks at 386 and 407 in the Raman spectra. So these peaks, actually, you look at here, this is for the monolayer, they are very close to each other, while for the bulk, they are far apart. Okay, so the gap between these two peaks will give rise to the identification of the layers, and these two peaks in the Raman spectra are related to these modes, which are like EG modes are related to the in-plane vibrations of the atoms, while the AG is related to the out-of-plane vibration of the atoms here. And you can see there is another Raman peak very close to the laser line, okay, which is bilateral and it is missing in the monolayer region actually, okay. So which shows that so this particular peak is related to the interlayer breathing mode of the MOS2, and this peak is missing in monolayer because there is no interlayer breathing mode here, okay. So this is how actually you can identify, and you can see the contrast in the optical images here, and these are actually the what do you call it, like the processed images for the grayscale contrast, so that you should be able to find out what is the right thickness, okay. And this has been actually calibrated with the AFM for the thickness also, so it's a well-known technique right now. Anyway, so I'll go over the interesting aspect of these materials. So as I mentioned that the monolayer of MOS2 has a direct band gap, okay, and it shows a very strong photoluminescence from it, okay. And the general understanding for these materials are that you see a lot of excitons in these materials, and what you see on the screen is, you see here the monolayer of MOS2, and this is the optical contrast from where we have identified, okay, this is the monolayer. And once you have the monolayer, we have done the Raman spectroscopy to characterize, and then the PL spectroscopy. Now you look at PL spectroscopy here. So this is the PL data. And what you see here is this, in general, the understanding for these materials are that there are three different kind of optical transitions here. So we call them as a exciton, B exciton, and A minus trion. So now what is this excitons are actually, okay? Once a light is absorbed by the semiconducting material or insulating material, so you have the electrons from the valence band go to the conduction band, and there is an electron hole pair generation now. And now because of the the Coulombic attraction between these two, actually they can travel from one place to one atomic site to the another atomic site. So they form the quasi-particles actually, okay. And these quasi-particles are because of the Coulombic interaction between the material as well as these two like electrons and holes. And so if you have an electron and a hole, then you call it as the quasi-particle bound pair of electron hole as an exciton. If you have two electrons and one hole, and they are like attached to each other by the Coulombic induction, you call it as a trion. So now this is a A minus trion. If you have two holes and one electron, then you say it is A plus trion or something, okay. So this is how actually you understand the exciton or the excitonic physics in these materials, okay. But you know that this is very interesting aspect, that you have one electron and one hole, okay, one positive charge and one negative charge, and this is equivalent to your hydrogen atom, yes. So but before I go over the analogy with the hydrogen atom, what we can see is that in the if you cool down, so this is the optical absorption of the gallium arsenide, okay, as a function of the energy. And what you see here is that this is the room temperature data, okay. So it falls down, and from the slope of this graph, actually you estimate what is the band gap of the material, okay. But if you cool down these materials, okay, so what you see is that there are some features which are appearing in the optically transparent region of these materials, and from where these features are coming actually. So these features are coming, so you know that the electrons jumps from valence band to the conduction band, okay, and then you have electrons here and holes here. Now in between the band gap, there are some energy levels, okay. These are the energy levels of the excitonic states, okay. And this is very interesting physics here, and this is equivalent to the hydrogen atom, yes. So you have a one electrons encircling the nucleus, which is the positive charge, and what you have is the various energy levels, okay. So now once you have this analogy, so you must have some energy levels, okay, and these energy levels are within the band gap of the material, and these are very interesting. But the energy scales of the hydrogen atom and these excitonic levels are completely different, because these excitonic levels have a very small energy in comparison to the hydrogen atom. But yeah, but you can just take the analogy. So you have the energy levels associated with the excitonic levels, and you have the excited states of the excitons. Okay, they lie right below the the bottom of the conduction line. So then you have multiple transitions coming out from this. Especially in case of this metal dichalcogenides, if you have this, you know that if you have a bulk, then the excitons actually can move. So the excitons are two different kind of excitons based on their energy as well as the length scaling, the separation between the electrons and holes. So if they are localized to a particular region, then you call them as a Frenkel excitons, and if they can move around in the material, then you call them as a Vanier mode excitons. And these excitons are very, very interesting here because you look at this picture, this is 3D excitons, because if you have a bulk material, they have a complete 3-dimension the Coulombic interactions. But if you confine them in a monolayer, okay, so which means like you call them as a 2D excitons, and they are very, very interesting because now the continuous spectrum here has a gap here. Okay, so this is the excitonic energy here, optical absorption, and then you have a gap here. This is coming because of the confinement of these the charge carriers, and this gives rise to a very, very interesting aspect of the physics. Okay, so you know that these excitons are associated with the excited states, and it's very difficult to observe them. And at the same time, if you keep these materials with the different kind of dielectric material, okay, or if you cap them with the material with different dielectric constant like hafnium oxide, hexagonal boron nitrate, you have a different kind of phenomena observed. And one can do the same kind of research as done by these people by changing the solvent in which the materials are with a different dielectric constant, okay, and then you have a different kind of physics involved because of the dielectric. So the dielectric screening is very, very important. Now coming back to the MOS2, so people have tried to understand whether you are able to see those excited states. For example, in WS2, people are able to observe this, the 1s excited state, 2s excited state, 3s excited states of the excitons, the ABC exciton, but in MOS2, it's very difficult. The reason being, in case of MOS2, the spin orbit coupling because of the molybdenum, okay, is very small. So which means the gap between the excited states are very small, and as well as this B exciton, which is coming because of, you know that, so the valence band actually splits up because of the spin orbit coupling of the molybdenum. In tungsten being like a higher atomic element, you have a larger spin orbit coupling there. So you are able to distinguish between these two energy levels. But in case of MOS2, since it has a very small gap, spin orbit gap here, spin orbit couple gap. Okay, so these peaks actually, the excited states of the A exciton, it is difficult to observe using the the normal photoluminescence spectroscopy or something. Yeah. So it is very difficult actually. Okay, but what we try to understand is that it is not only the so the gap, spin orbit gap is large in WS2, so we are able to see the excited state of the A exciton in WS2, but it is difficult to see in the MOS2. And it is not clear. There is an ambiguity in assignment of the A- trion and A exciton peaks. Okay, you can see that there is, this is kind of published in this particular paper, and a lot of people have tried to understand it, and it's very difficult to distinguish, particularly for MOS2, where this A- trion will be there and where the A exciton peak will be there. Okay, so what we have done just the we build up our understanding by doing the low temperature Raman as well as the PL spectroscopy. So what you can see is this is the general understanding. So at 300 Kelvin, you have a A- trion, you have a exciton and B exciton. That's all actually the people actually report. Okay, but when we have cooled down the sample down to 4 Kelvin, what we have seen is there are 6 different kind of transitions which are appearing, and if we look at the temperature dependence of these transitions, okay, so they show the electron phonon interactions are visible, but there are some peaks which are lying only up to certain temperature and they disappear. And so this is very interesting actually. Okay, so instead of 3 peaks, there are 4 actually going up to the room temperature, and we try to understand it. Okay, so let me go back here and then tell you. So this is the A minus trion, this is A exciton, this is B exciton. So what are these D1, D2 and D3 actually? Okay, so these are the peaks which are coming at low temperature, and actually certain peaks are actually existing up to the room temperature also. So first thing is that what one can do is you can do a power dependence photoluminescence spectroscopy. So what happens is if you have some defects in the sample, then these defects actually will saturate first, then the other optical transition. So if we look at here, so this is relative integrated PL intensity. You see there is a black curve which is going down, rest of the other curves are actually going up actually. So now if you have excitons which are bound to the defects, okay, so there you will be, so these are the very minor defects you will be having in the sample, and those excitons which are bound to the defects actually will give rise to these optical transitions. So we have tried to understand that, okay, this is particularly coming because of the sulfur vacancy bound exciton. Okay, now if you look at the molybdenum vacancy can be there, but it is very difficult actually to, which is very rare to get the molybdenum vacancy rather than the sulfur vacancy. And we also have done the understanding of the PL peak, the FWHM versus the laser power, and what we have understood, there is a power law of the intensity of the D2 peak, okay, as a function of the intensity of the A trion. And if the slope of this curve is more than 1 or between 1 to 2, then there is an exact existence of the bi-exciton. So if you have large number of excitons in the semiconducting material, they might interact with each other and they might form the bi-exciton. Okay, and this is a very, very interesting aspect of this particular research, where the existence of the bi-exciton up to the room temperature have been proposed. Now, what we have done is, based on the 4K data, we have proposed the energy level diagram. So this is the valence band and this is the continuum, which is the continuous, like the conduction band here. Now the various transitions, we try to map it. So now this is 1.8 eV, which is D1. Actually, this is the defect bound sulfur vacancy defect bound excitons here. And we have 1.90, which is coming because of the bi-excitons, and then you have A minus trion and the first excited states of the A exciton, and this the second excited state of the A exciton here. And here what you see here is that the B exciton. Okay, and while we were actually studying this particular aspect of this monolayer, there was a research published in this particular paper where they have also identified that the second excited state of the A exciton, okay, will appear 175 MeV above the 1s exciton. Okay, so just 1.175 milli-electron volt above this one. So this is actually which supports our data and confirms that, okay, we are able to observe this excited state of the molybdenum disulfide. So what we conclude from here is that so the general understanding of the room temperature, where only 3 peaks are existing, okay, there are more optical transitions, there are more optical phenomena which are happening, particularly in monolayer MOS2, where you have the bi-excitons which are existing up to the room temperature also. So this is very, very interesting aspect of this particular research. So these excitons have the applications in like there are various applications for it. Okay, for example, the excitonic LED. So you can have a light emitting diode because of the excitons here. You can understand the many interactions of the multifunctional or the multi-excitonic states here. And you can see that these materials are very good to understand the Purcell effect, where you can enhance the rate of the optical transitions or the optical emissions because of the environment. So you can see here. So these are the silver nanowires which are put close to the MOS2. So if you have no edgy nanowires, okay, you have a very limited rate. But if you have a edgy nanowire very close to it, so like the proximity of the materials will change. Sorry. Yeah. And what you can create is actually like the valley LED, which is one of the interesting aspect of these materials, the valleytronics, where you can control the spin of the electrons in the valleys of the valleys of the band structure, and there you can actually you can distinguish between the like the different kind of spins in the spin up and spin down at different values, okay, and you can have a spin polarization there also. So these are very interesting aspect, okay. You can use this excitons for quantum information processing, quantum logic gates, photonics, bi-exciton lasik devices, and terahertz applications. So there are several applications in for these materials, okay. If we are able to produce these materials in a large scale, okay, then you have a lot of technological applications because they are versatile, they have like flexibility, they have optical transparency, they have a thickness tunable band gap, and one can do the gate coupling, okay. And if you have a monolayer, then it has a high carrier mobility also. So you can create a lot of applications, okay, that includes like the flexible solar cells, biointegrated electronics, flexible displays, RFIDs, okay, wearable electronics, electrochromic windows, sensors, and there are several biomolecular biomarkers. The biosensing devices one can make it, okay, and these are very, very interesting materials for flexible electronics. Okay, so this is the story about the MOS2. How much time I have, Chair? Hello.
Hello.
Can I? Yeah.
You can continue till 5 more minutes.
Okay, so 5. Okay, I'll just share another 2-3 slides actually. Okay, there's another material for the photovoltaic, which is the chalcogenide perovskite materials, which is kind of in like it is adopted from the oxide perovskites, okay, because these materials have the band gap in the visible region, so they have a very interesting aspect. Now, when we talk about the photovoltaics, what we know about it, like the light falls on the material and there is an electron hole pair generation, and then you take out the electrons from one end and the holes from the other end to the external circuit, and then you have the electricity generated from from the light, okay. And for several decades actually, okay, silicon has been one of the best photovoltaic material, but last 4 or 5 years or something, people have been looking for those materials which are like the perovskite materials, which shows very nice response to the light, okay. And following that, chalcogenide perovskite is a recent material and advanced material which shows the similar kind of activity. And we also try to understand what is the mechanism actually, okay. We have a collaborator in RPI Troy who grow this film, very nice films, and they have done the measurement on the devices, okay, which I will show. But let me just go over that. The perovskite chalcogenides have the formula like ABX3, where A is alkali and alkaline materials, rare earth materials. B is a transition metal, and X is a chalcogenide. And these materials are very interesting because of their structure, as well as the band gap. Okay, so you can see a series of the material chalcogenide perovskite. And what is important here is that if you have a distorted structure, okay, that is more useful for the photovoltaic application. Another interesting aspect of these materials is the stability, because you know that if you are going to have a photovoltaic material or solar cell, you are going to keep it in the environment outside, and you don't want that material to degrade, okay. And so they have to be environmentally stable, okay. So BAZRS3 lies here. So this is the work done by the RPI group, where they have shown how this BAZRS3 film actually shows the stability towards the surrounding or the environmental effects. And they were able to show that very nice device on the photo detector characterization and performance. And what they have shown is that the photo detecting device with the photo responsibility of around 46.5 milliampere per watt, kind of, and that's what. And what we have done is we try to understand how these vibrational properties, okay, or these materials, how we can improve or enhance the photovoltaic response or the photo response of these materials. So you know that this is a distorted structure. So now, and another aspect for these materials to become a good photovoltaic is that they are antiferroelectric in nature, which means you do not have an internal polarization which can actually separate out the electrons and holes, or which can keep it for a longer time. So we have done the low temperature Raman studies and to understand what is happening in the structure which is supporting particularly this particular material. And we try to understand the complete phonon dispersion and the phonon vibrations of the atomic vibration in these materials. And what we realize that these materials are interesting because the structural distortion, especially the rotational modes, are important to create ferroelectricity in these materials. Now, once you have a ferroelectricity, that means you have a finite polarization. Now, that polarization will help the electron and holes to be separated from each other and keep it in the material for a longer time, with longer duration. And this is where actually we try to understand that how this distortion helps it. Okay. Now, these materials have been grown from the oxide material. So what you do is you sulfurize the barium zirconium oxide at certain temperature in the presence of sulfur. So you have some impurity oxygen. Now this impurity oxygen will distort the structure as well as it will create the center of invergent symmetry. Like it will break the symmetry, invergent symmetry, and that particular will give rise to the polarization. And what we have estimated from our calculation that the polarization is this much, like 0.6 microcoulomb per centimeter square, which is very interesting for these materials. All right, and that helps actually for these materials to be a good photovoltaic material. So let me summarize that the study of light matter interactions is a good platform to understand the fundamental physics for the technological applications. Chalcogenides, layered chalcogenides are very good materials for studying this optoelectronic and photovoltaic devices. And the understanding of the excitons is important for the various application. And BZRS3 is a good photovoltaic material. Before I conclude, let me just thank the people who have been involved in this particular research. So what I have shown, so this is my group at IIT Mandi. So I have like several PhD scholars as well as master's scholars. And the work which I have presented is done by Dr. Juhi, who has graduated last month. And I would like to thank the collaborators, especially Professor Korakar from PI and from several collaborators from India, Professor Tarafdar and other people. And I would like to thank the funding agencies also. I'll be happy to take the questions. Thank you very much for listening, and I'm really thankful for a very nice conference.
Thanks a lot, Dr. Soni, for excellent presentation. May I request audience, if they have any question, feel free to ask. We may take 2 to 3 questions, please.
See, the online platform has this is a hard difficulty actually. It is monotonous. The speaker speaks, and most of the time you don't have questions actually, especially from the class also we have it. So in case anybody has a question afterward the sessions, I will be happy to answer over email. So you can drop an email to me.
Yeah. Yes, you rightly said, Dr. Soni, there are different challenges and of course opportunities also when you are delivering lecture in an online mode. So thanks again for wonderful presentation.